If we divide them equally among 4 boxes, how many apples will be there in each box? It's easy to find out, isn't it? 22 is equal to 4 times 5 plus 2. Each box will have 5 apples and there will be 2 apples left in the basket. As you can see, for the 2 positive integers 22 and 4, there exist 2 integers 5 and 2, such that 22 is equal to 4 times 5 plus 2. Can we find 2 such integers for any 2 numbers? By dividing 14 by 3, there exist 4 and 2, such that 14 is equal to 3 times 4 plus 2. Hence, Q equals 4 and R equals 2, Q being the quotient and R the remainder. Similarly, by dividing 27 by 5, there exist 5 and 2, such that 27 is equal to 5 times 5 plus 2. And by dividing 38 by 9, there exist 4 and 2, such that 38 is equal to 9 times 4 plus 2. And by dividing 53 by 6, there exist 8 and 5, such that 53 is equal to 6 times 8 plus 5. So for any 2 given numbers, there exist 2 integers based on certain conditions. What are those conditions? Let's find out. What can you say about quotient and the remainder in each of these examples? Are they unique? Yes. For 2 given numbers a and b, there exist unique q and r, such that a is equal to b times q plus r. What can you say about the remainder? Can it be negative or greater than b? No, the remainder is always positive and less than the divisor. If a and b are 2 positive integers, then there exist 2 unique integers q and r, such that a is equal to b times q plus r, where 0 is less than or equal to r, which is less than b. This is Euclid's division lemma. Can a and b be negative integers? Yes, Euclid's division lemma can be extended to all integers. Let a and b are any 2 integers where b not equal to 0. Then there exist unique integers q and r, such that a is equal to b times q plus r, where 0 is less than or equal to r is less than modulus of b. Let's look at an example. For 2 integers, minus 18 and 5, there exist 2 integers, minus 4 and 2, such that minus 18 is equal to 5 times minus 4 plus 2. A lemma is a proven statement, which is used to prove another statement, while an algorithm is a set of well-defined steps which gives a procedure for solving a type of problem. Euclid, a famous Greek mathematician, designed an algorithm to find the HCF of 2 integers, which is known as Euclid's division algorithm. Let's find the HCF of 18 and 12 using Euclid's division algorithm. First, we use Euclid's division lemma to write 18 as 12 times 1 plus 6. Note that we divide the bigger number by the smaller number. Since the remainder is not 0, taking the divisor and the remainder, we apply Euclid's division lemma one more time. The remainder is 0. We cannot proceed any further, so we halt the process here. The divisor at this stage, that is 6, is the required HCF. Euclid's division algorithm is defined as follows. Step 1. Divide A by B. Note that A is greater than B. By Euclid's division lemma, there exist two integers q and r, such that A is equal to B times q plus r. Step 2. If r is 0, the divisor B is the required HCF, and if r is not equal to 0, replace A by B and B by r and repeat the process. Repeat this process until the remainder is 0. Let's find the HCF of 2020 and 450. Consider the bigger value as A and the smaller value as B. Divide the value of A by B. By Euclid's division lemma, there exist q and r such that A is equal to B times q plus r. If the remainder is 0, the divisor B is the required HCF. If the remainder is not equal to 0, replace the value of A by B and the value of B by r and repeat the process. Since r is not equal to 0, replace A by B and B by r and repeat the process. By applying Euclid's division lemma again, there exist q and r such that A is equal to B times q plus r. Since r is not equal to 0, replace A by B and B by r and repeat the process. By applying Euclid's division lemma one more time, we find that there exist q and r such that A is equal to B times q plus r. Since r is equal to 0, stop the process, and the divisor B equals 10 is the required HCF.